Welcome to section 2.2. We're going to talk about conditional statements. We're going to build on what you learned in 2.1. In fact, we're going to start by reviewing a little bit from 2.1 and take that directly into implication and biconditional or conditional statements. We'll talk about necessary versus sufficient because this is kind of an important idea. And then we'll represent logic in computers. So let's review composite statements from last time. A composite statement is when I have two statements that are connected by one of the logical connectors. We actually use this example, but we never used the actual if-then connector anywhere else. So we kind of left this hanging. That's what today is about. We actually talked about these connections, and we talked about negation, conjunction, disjunction, and exclusive or, and we left the last two for us to talk about now. And that's kind of an important detail because that's what we're going to focus on today is implication and biconditional. So let's start with implication. Implication, again, I start with two P's, a P and a Q. It's true if P is true, and as long as P is true, excuse me, it's false only when P is true and Q is false. It's true otherwise. So in a truth table, it looks like this. And let's just talk about this truth table for a second. They're both true. If true, then true. That makes sense. If true, then false is false. Okay, but this is where these last two are where it throws people off. If false, then true is still true. If false, then false is still true. This is where it's important for you to understand this distinction. These statements are only valid if the if-then statements actually execute. And we call the if part the hypothesis and the then part the conclusion. Now, we don't have to use an if-then statement. This implication can actually be written a whole lot of different ways. For instance, I could write this traditional if-then, if P then Q. I could also write P only if Q. P is sufficient for Q, Q whenever P. For instance, I could say if the Cowboys won the Super Bowl in 2023, then 2 is prime. Standard if then. If you complete all your homework in the class, all your homework assignments, then you'll pass the class. Now, these statements, again, in and of themselves, they're broken up into the true and the false portions of it. And we can talk about each of the chunks, the if part and the then part, and seeing if they're true and testing those, and then testing if there's any problem. Turns out this statement down here, so this first one, many of you actually know who the Cowboys are. They did not win the Super Bowl, yet 2 is still a prime number. So this statement's actually a true statement. If you complete all your homework assignments, then you will pass the class. That is not necessarily true. It is possible you can complete every homework assignment and not do a single test, which would automatically fail the class. So because this is actually a false statement, now I will be 100% honest with you. Your likelihood of passing class probability, and so we're getting to probability, not logic, is much higher if you actually do all your homework assignments, but that's your call. All right. So variations, we have something called the converse, the contrapositive, and the inverse. Now let's just look at these. The converse, I just switched the order. The contrapositive, I switched the order and I negated both of them. And the inverse, I just negated them. It turns out, so just to look through this, if I took something like if it snows, then the traffic moves slowly. The P in this situation is it snows. Q is traffic moves slowly. So P implies Q. We've done that. But the converse, that's this first one, would be if the traffic moves slowly, then it snows. Notice that this is not necessarily true. So because there could be a lot of other things that cause it to be slow. So because of this shows us that converses, while it could be true or P implies Q could be true, the converse is not necessarily true. And so converse is not the same. Similarly, I can take the same statement, the contrapositive would be if the traffic does not move slowly, then it does not snow. Okay, we could actually take that to be true. The inverse, again, I keep them the same order, but I negate them. So if it does not snow, then traffic moves quickly. the opposite of slowly. So we get these ideas, we can move through it and practice. And the big thing about this again, and I'll just tell you right now, I'm going to spoiler alert, is that these two, is that the converse, where's my pen? There it is that these two are logically equivalent, meaning they are true at the same time. On the other hand, are contrapositive and P implies Q, those two are logically equivalent. So this is going to be important later on because sometimes it's easier to make a statement using the contrapositive than it is to do using the original statement. We're dealing with if, then, and so forth. All right, let's talk about biconditional for a second. So biconditional, it looks very much the same, except we got two arrows. And we say that if and only if, or sometimes you abbreviate this in books and it says IFF. It's only true if they're both the same value. So they're both true or both false is the only time that it is true. A biconditional statement is really, really powerful. Truthfully, it's actually two conditional statements, two implications put together. So we now have our five biconditionals we don't talk a lot about in this class, but they will come up just a little bit. So I'm just throwing it out there. So we now have our five connections. So let's talk about order of operations of these. If there are no parentheses, parentheses always take precedence. We then apply negation. And then we apply the and or. These come second. And if they're both present, you obviously need a bunch of parentheses to dictate what's the order. In general, we actually do these, and we get what are called clauses. A clause is where two things are connected together, and then that clause is connected to something else. This is used all the time in what's called two-sat programming, because we use computers love to use Boolean or logic to test certain things. And last but not least, we apply the arrows. And again, if we have both implication and biconditional, we're going to need, even if we have multiple implications, we're going to need some arrows some parentheses to break this apart. So in general, use all the extra parentheses you can. All right, so let's just look at an example. I want you to make a truth table for this P implies Q and not P if and only if Q. So to make a truth table, you're going to need a lot of different things. You're going to need P and Q because we have those. We have not P. Notice we don't need a not Q because we have no not Q in here. I have to find P implies Q. I have to do the not P if and only if Q. And then I can do the whole thing combined together. Go ahead and pause the video and you fill out this table. All right, so if you did that, your table ends up looking like this. Not P is obviously the opposite of P. P implies Q is only false in this situation. Not P, so now we're looking at just these two things. When are they both true and when are they both false? Well, that's these two middle ones and false on the outside. And I'm now just looking at these two things and saying, is false? They're both false. One's false. Okay. One of them's false. We get here. Hey, they're both true, true, false. So we get this situation right here, which is all true, only true when P was false and Q was true in the first place. So that's kind of an invaluable insight into all this together. All right, let's transition a little bit. Let's put it now, take it from words and put it into symbols, because this is cool to have symbols. These are really easy then to make tables. But suppose I give you the sentence, if you're older than 13 or you have your parents with you, then you can attend a PG-13 movie. Well, we need to break this up into the statements that we can use. So notice if I break it up to put some parentheses and some things, I now have situations where I can say, okay, I can say that P is if you are older than 13. Q is you are with your parents. R is you can attend a PG-13 movie. With that knowledge, we can now rewrite this as P P or Q implies R. If you wanted to go a step further on this, writing it to make it super clear, I would just add parentheses. Namely, I would do parentheses around the P or Q, just like we have parentheses up here around the statement. So when we're parsing these things out, we notice I even took the minute to write this down. And that's the expectation. We kind of be direct and clear and not just assume that everyone knows what we are implying. If in logic, if it's not clear, what might be clear to you is not necessarily clear to someone else. So you have to make sure it's completely clear to everyone in the process. All right, let's practice another one. Some general rules are that you want to look at a couple things. Like if I did this one, this is talking about another university, I pulled this off their website. They get free coffee if you're a student, it's Thursday. So it's simply Q and R, where Q is if you are a student and it's Thursday, then, because notice the if part is actually the latter part. That's the catch. Let's try another one. Do a speeding ticket one. I like this one. I'm actually telling you that P is you drive over 75 miles an hour, and Q is your speeding ticket. So I've already given you the statements. Okay, I want you to translate these statements, 6 statements. Pause the video. Can you write them as logic? All right, so hopefully you did. Let's break them down one at a time. You do not drive over 75 miles an hour. That is a not P because we're negating the P. You drive over 75 miles per hour, but you do not get a speeding ticket. Now, the question is, what is the but? Really, it's connecting these two things, meaning I'm driving over 75 miles an hour and I did not get a speeding ticket. So that is actually a P, driving over 7 miles an hour, and not Q because I didn't get a speeding ticket. You'll get a speeding ticket if you drive over 75 miles an hour. Notice the if part is the 75 miles an hour, so that is P implies Q. If you do not drive over 75 miles, so notice is a negation of the P. It's the if, so we have not P implies not Q because not get a speeding ticket. Driving over 75 miles an hour is sufficient for a speeding ticket. Now, this goes back to what we had before. Meaning, if I'm driving over 75 miles an hour, that implies automatically that I get Q. So the same thing as if driving over 7 miles an hour, then you'll get a speeding ticket. So this is where the term sufficient. Sufficient means it is enough. It doesn't mean it's the only way, but it is will get you it. You get a speeding ticket, but you do not drive over 75 miles an hour. That would again be an and statement. And I do Q because we did get a speeding ticket, but not P. And then you're probably really frustrated. So this is how we break these things down. We have to be able to translate them into this notation. All right. Now I mentioned sufficient. Let's talk about necessary versus sufficient. This is kind of something important. P and Q are propositions. P is a sufficient condition for Q if whenever P is true, then Q is true. But notice that doesn't mean that Q has to be true if P is true. It's just saying if P is true, then Q is true. Well, let's think about that. What is a sufficient condition for it to snow outside? That's been something that people think about. Sufficient, it is sufficient if you look outside and the temperature is at least at a certain degree. So if the temperature, if it's snowing outside, then it's sufficient to say that it's, so if I say it's snowing, then there is a temperature, but that temperature could occur without it snowing. That's the idea of sufficient condition. However, necessary conditions are things that if they are not met, then the latter does not occur. And the interesting part is it actually swaps it. So a necessary condition is something that must occur in order for something to be true. So I want you to think about this class. What are the necessary and sufficient conditions to be in this class? Well, sufficient, if you are a computer science major, then you take discrete math. Okay, but does that mean that only the only students in discrete math are computer science majors? No. So it's not always the same. Here's another one. The sum of two positive integers is positive. What's the hypothesis and what's the conclusion? The hypothesis is that two integers are positive. The conclusion is their sum is positive. And thus, and the necessary condition is the sum is that the sum being positive is necessary for the integers to be positive. What I mean by that is if the sum is not positive, then I know that my original two things I added together were not positive. However, if my two integers are positive, then their sum can be positive. Think about this for a second. Can you take two integers that are not necessarily positive and have their sum be positive? Yeah, sure, we can. I can think of one right now. I can go 3 plus -1. Well, that's equal to 2. Well, this is positive, this is negative, and this is positive. So that's a situation where I had a positive sum, but this portion was not taken care of. That is why the if part is the sufficient, but it is not necessary. The only time that they're both necessary and sufficient is an if and only if situation. In other words, a biconditional. So that is the kind of the idea we have to use. All right, let's talk about computers for lastly, and let's wrap this up. So Boolean arithmetic, computers use what's called Boolean. I don't know if you know this real quickly. When Boole actually came up with Boolean algebra, he was quoted as saying, finally, I came up with something that no one will ever be able to apply. This is the lesson. Mathematicians have been coming up with stuff for years. And often we have to understand the pure math to understand how to apply it. If we focus only on applications, then we actually cut ourselves off and never get to the new and powerful things that will actually change the world. So that is why pure math, or in other words, math that it does not necessarily have a direct application, is not bad. So I may give you stuff that you're like, I can't see an application. That's okay. Doesn't mean you won't see it in the future. So a Boolean variable is a variable that takes on a 0 or 1. And not 0 is equal to 1, and not 1 is equal to 0. So there's your negation. We can add them. Now, 0 plus 0 is, well, 0. 0 plus 1 is 1. 0 plus 1 is 1. And 1 plus 1 is 1. Wait a minute. This is the part that throws people off. The reason is, and I'll tell you in a minute, this is, if you looked at the table of OR, where 0 was false and 1 was true, you would get exactly the same thing by combining true and false for ORs. Similarly, if we do multiplication on them, 0 times 0 is 0, 0 times 1 is 0, 0 times 1 times 0 is 0, and 1 times 1. And yes, order does matter in different algebras. That's why we care about this and we write it down this way. So computers, they take a bit, which is a 0 or 1. They create a bit string that's zeros and ones. And the length of that string is how many bits are in it. We define 1 as being true and false as being 0. Then we change a couple things. Negation becomes a bar over the top. Addition becomes the or symbol. And multiplication is going to be the and symbol. And that is actually where we get to do some cool math. So if I wrote this, there's a typo in here. I hate it when the computer doesn't do what I want it to do. So let's put a bar over all of this. It's not just over the 0 in the middle. The negation of this actually literally changes each and every one. So this 1 becomes a 0. The second one becomes a 0, and so forth. So it swaps all the bits. So that bar, which we'll talk about in sets later on, is called the complement. Now, what if I do this one? Again, I'm using which symbol? Well, this is an or symbol. And now we add them place-wise. So I have a 1 plus a 1, that's a 1. 1 plus, I'm sorry, 0 plus 1 is 1. 1 plus 1, 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 1, and 1 plus 1 is 1. So I get 1, 1, 0, 1, 1. Now this is easier. I wrote it this way, but the easier way for us, if I was to write this out, that would make this even easier to do, is if I literally wrote them vertically. So I did 1 1 0 1 0, and then I did the 1 0 0 0 1 with the or. And then I add them down and see a 1 1 0 1 1. So bits love this in that we can go ahead and work on them very clearly and just operate on them using all these things. So with that said, what is this one? What is that? Go ahead and pause the video, find it yourself. All right, you should get one with 4 zeros after it, because notice the only time you'd get a one is if they're both ones, and that only occurs in the first spot. Now, I did not even mention exclusive or. Ah, this one is funky. But remember, exclusive or is true if exactly one of them is a one. So the funny part is what that means if they're, let's look at this. Let's again write them vertically so you can kind of see how this one would work. But it's going to use the exact same idea that we've already just done. So I have one. Oh, sorry about that. My pen just kicked out on me for some reason. We have a 1 1 0 1 0 and 1 0 0 0 1. Well, exclusive or is a one if only one of them is a one and one of them is a zero. So the first pair we have here, that's going to be a one, that's going to be a one, that's going to be a zero, that's going to be a one, and that's going to be a zero. So this is actually where it gets kind of crazy, and we can actually utilize a couple different options to see this and utilize it. So your computer loves to use bits. You can play around with this more. I didn't even get into something as to how it does some different things with negation and so forth, because we can iterate. But this is the general idea that's utilized. You further use this for things, again, like I mentioned, we use for a lot of two-sat or two-satisfactory. These are known as polynomial search algorithms. They're very powerful and wonderful. Um, one of my papers I published a couple of years ago in a computer science journal created one of these and utilized it to, because I show that it was held true. Therefore, we know a lot of things about our finding. All right. Good luck. Let me know what questions you have.